Welcome to this puzzle Kickstarter session. We will continue with our discussion on well-ordering principle. So let us recall what is the well-ordering principle. So the well-ordering principle says that every non-empty subset of the natural numbers has the smallest element in it, which means that if S is a subset of natural numbers, S non-empty, then there exists an element little s in capital S such that little s is at most t for all t in S. So that's what that means. And let us recall, or rather, let us look at an abstract template of reasoning that we employ when we use the well ordering principle. So suppose this be a mathematical proposition. How come such a thing be called a mathematical proposition? Well, consider a mathematical statement which is indexed by natural numbers. For instance, you can consider statements like, trivial statements like every natural number is either odd or even. That's a mathematical statement which is indexed by natural numbers. So for such a statement, the answer would be yes if that statement is true for a given natural number, and no if that statement is false for that given natural number. More non-trivial examples would be something like, let's say, for all graph on n vertices, where n is any positive integer, such and such thing is true. So some statement about graphs is true. Or it could be for all graphs on n vertices which are connected, such and such thing is true. So there is a abstract way of expressing what a mathematical proposition is, and this is an abstract way. So fix some mathematical proposition. And suppose we want to show that this is true for each n, meaning it takes the value yes for each n. Right? So here is one approach to showing it, and here is where we use the well-ordering principle. So somehow show that f of 1 is yes. Usually this is just a computation. So this one can establish by force. Then consider B, the set of all the quote-unquote bad natural numbers. So these are those natural numbers for which the proposition is false. F of n is no. And assume there is at least one bad element. So this is non-empty. So this is in contradiction to what we want to prove. We want to really prove that this is empty because we want to show that f of n is yes for all n, which is to say that there is no bad natural number, which is to say that B is empty. But we assume on the contrary that B is empty. And now by well ordering principle, we use we can find some n naught, which is the smallest element of B. Okay, and by the base case, this n naught cannot be equal to 1, because if n naught were equal to 1, then since n naught lies in B, we would have f of n naught is no. But we've already seen that f of 1 is yes by pure computation. So n naught is at least 2. And then typically what happens is we end up showing that n naught minus 1, which is a natural number because of this line, is also bad. And that's a contradiction to the minimality of n naught. So this contradiction would establish that B better be empty. And I'm not trying to say that this is the only way to use the well ordering principle, but this one particular template of reasoning essentially captures how the well ordering principle is used. So the point of this lecture is to see one example, some relatively complicated example compared to what we saw the last time. So here is the problem. So fix some natural number n, and suppose we have n plus 1 bins. Bins are just some boxes where you can put things. And each bin has some number of balls in it. Right, so there are these bins, and each bin it could have 0 balls, meaning no balls, or some finite number of balls in each of the bins. Okay, and here is the game. At any step, one is allowed to choose n bins and add 1 ball to each of these n bins. So I could pick the first n bins and put 1 ball in each of them. I could do that, so this is allowed. And what we want to show is that it is possible to have the same number of balls in each bin after some sequence of such steps. So one can choose your steps, every step you have to choose n of these n plus 1 bins. And you can do this in an intelligent way so that at the end of your procedure, meaning after finitely many such steps, you can achieve equality in terms of the number of balls in each bin. So that's an interesting proposition, and we want to prove it. So here is how we will. So the solution will use the well ordering principle. So clearly for n equals 1, you have just 2 bins, and you can choose one of the bins and put 1 ball in it. So whichever bin has fewer number of balls, you can repeatedly add balls to it so that you get equality. So for n equals 1, this is trivial. This is the base case. and let b equals those natural numbers for which the proposition or the statement is false. So these are those natural numbers for which you can, so that if you have n plus 1 bins, and so these are those natural numbers for which there exist n plus 1 bins with some initial configuration of balls in them, meaning some choice of number of balls in each bin, with the property that you cannot possibly equate the number of balls by just executing the step that is allowed, this particular move that is allowed finitely many times. So these are all the bad natural numbers, and let n naught be the minimum smallest bad natural number, which is where we use the well ordering principle. And we want to somehow create a contradiction. Yeah, so assume that this is non-empty. If this is empty, then we are done. So assume this is non-empty. Okay. So here is the thing. We have, let me copy this. So we have n naught plus 1 bins. So these are total of n naught plus 1 bins, and let's say these are total of the first n naught bins. This is the last bin. So total of n naught bins here, and then one more bin. So n naught plus 1 bins. And there is some number of balls here, some here, some here. Let me also give that a name. Maybe b1 balls here, b2 here, and so on. Right? And of course, this configuration is chosen such that there is no way to equate the total number of balls in each of the bins using that move, and we want to somehow create a contradiction. Okay, so here is the thing. We can choose any of these n naught bins and put one ball in each of them. So here is what we can do. We will choose this bin and n naught minus 1 bins from this part. So every time we do that, this bin will have this bin will have one more ball, and some of the n naught minus 1 bins here will have incremented by one ball each. But the main point is that n naught minus 1 is not bad, simply because n naught is the smallest bad natural number. So n naught minus 1 is not bad. Therefore, these bins, which is n naught minus 1 plus 1, these n naught minus 1 plus 1 bins have the property that if you intelligently choose in each step some n naught minus 1 bins and put one ball in each of them, you can equate the number of balls here, right? So whatever is that choice of the sequence of n naught minus 1 bins every time, that is a mystery. This is the power of induction. We can make all of them equal, and in the process, this will get added. The number of balls in this bin will get incremented by the total number of steps that we require to equate the amount of balls in each bin. So after doing that, so we have exploited the well ordering principle. After doing that, what we will have is we will have a configuration where each of these are the same number, call that b, and this is some other number, let's say b prime. Okay, so there are two cases. One case is b is less than b prime, right? So what do? We need to argue that somehow we can also make things equal. This is very easy, actually. So we can choose any of these n naught bins, right? We can choose any of the n naught bins. So what we will do is every time we will choose these n naught bins. So every time we choose it, we will add one ball to each of them. So this becomes b plus 1, then b plus 2, and so on. And we'll do this as long as the number of ball in any of these bins is smaller than b prime. So just execute, choose the first n naught bins each time for b prime minus b naught steps. And then at the end of that, each of these bins will have b prime balls, and therefore we would have equated the total number of balls in each bin. Case 2 is So this is not proper. Case 2 is b equals b prime. Well, in this case, we are already done. There's nothing to do. The total number of balls in each bin is already equated. Case 3 is b is greater than b prime. Okay. So actually what we will do here is we will reduce this to case 1. So here we have more balls and here we have less balls. So cyclically choose n naught minus 1 bins here and one this and the other bin, the remaining bin to be this one. So what I mean by cyclically, I need to explain. Let me explain that by an example. So suppose we had 3 bins here and then this extra bin. So I'm arguing for n naught equals 3. And here, let's say you have 5 balls, 5 balls, 5 balls, and here, let's say you have 3 balls. So what I'm trying to say is that in first step, you choose these 3 bins. Next step, you choose these 3 bins. And in the next step, you choose these 3 bins. So after we execute these 3 steps, this will become 7 balls, this will 7 balls, this will 7 balls, but this will be 6 balls. The total number of balls, on average, each bin is not incremented as much as this one is incremented, because every time this bin is incremented by at least 1, but not every time this bin, for instance, is incremented by 1. This is incremented by one less number of times we employed our step. So we do this one more time. This is our first step, then second step, then the third step. In that case, this will become a 9 balls, 9 balls, 9 balls, and this will also become 9 balls. And they will be equal. So that's how one can tackle this case. Yeah, so I said that we will boil it down to case 1, but we didn't. I mean, we can just constructively actually deal with it. So I hope this was clear. So what we have contradicted is that n naught is actually not bad, because if n naught is the smallest bad number, n naught minus 1 is not bad, which we exploit to get to this configuration. And then via some reasoning, we have argued that actually this configuration can be equated via the allowed step. And that's it. So that's the end of the proof. And this is a non-trivial example. Okay, so I hope we appreciated the power of the well-ordering principle. As usual, like, comment, share, subscribe. Also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.